All right, welcome. In this video, I'm going to be recapping Calculus BC Unit 7. And that's, the unit that goes off of the second fundamental theorem of calculus, accumulation functions, really functions defined by integrals. Okay, so, the biggest of pictures, that is not in the show. 7.1 was second fundamental theorem. And that was where we learned how to take the derivative of an integral, really. So it's like the derivative with respect to x of the integral from some number up to x of f of t dt, that's equal to f of x. That was what we learned. Okay. That opened up a whole library of problems, derivative-like problems that we could do. Tangent lines, first derivative, second derivative, where is the function increasing, where is it concave down, where is there a point of inflection, where is there an absolute maximum, where is there a relative minimum. All of those good questions came from that. And I might have a nice example of this, because this is very free response friendly. It's very likely that when you take the AP exam in May, your third free response question will be one of these. And in 7.2, we looked at rate n problems, like looking at totals as an accumulation of rate. And so that would be, I think the big thing was f of b equals f of a plus the integral from a to b of f prime of x dx. This is really just a restatement of the first fundamental theorem. Okay, we also learned that we can get a total by integrating a rate over time. So, if we had a rate at which we were dumping water into a bucket and we wanted to know the total amount of water we had dumped into the bucket between time 1 and time 3, we would integrate that rate from 1 to 3. And then in 7.3, we did rate in and rate out. And so, in a lot of ways, it was very similar to 7.2, except we just added, I was dumping water into a bucket, and simultaneously the bucket was leaking. So there were kind of 4 key facts there. I'll different color. And make sure it's working. It's not. All right. So the first fact was that you can get a total in and a total out by integrating your rate in and your rate out, respectively. And same for total out. All right. We learned how to write a total function. So oftentimes these are also free response questions, and they give you the rate in and the rate out, and they ask you about the total amount at some time, or what is the maximum amount or something, and you have to cook up that amount function yourself. But really, that's that f of b equals f of a plus the integral from a to b of f prime. So the total amount, which I might call a of t, sometimes we call this n of t for the number of, especially when it was like whole things like cars or people or something. And sometimes you might see somebody call it q of t for like the quantity instead of the rate, but I'll just call it a of t for now. It's going to be the amount at some given time. Oftentimes that's time t equals 0, but not always. Right? They might give you the amount of water that started in the bucket that I'm dumping into and is simultaneously leaking. And that would be a of 0 if they gave you the starting value. But I don't want to just tie myself to always having to start at 0. We can start at any time. And this is where we will be integrating rate in minus rate out. And, okay, well, t is already committed, so I'm going to just call it x there. Right? And then the fourth fact is really just, again, a statement of the second fundamental theorem of calculus, is taking the derivative of a of t. So I don't like to say the net rate of change of the amount is equal to rate in minus rate out. Also, we could say that that's, where I take a prime of t by, okay, a of t0, that's some number, so the derivative of a number is 0. And then we know how to take the derivative of these. We take the upper bound of integration, we throw it in wherever we see the dummy variable. Well, rate in would probably be like f of x minus g of x. So it would be f of t minus g of t, rate in minus rate out. Yeah, that's all of it in the big picture. Now I'm going to dive in and look a little closer at each of these things. What else? The free response questions.
Like this. And I was just going to ask, so anytime I ask anything that will be a number to me as a derivative, you'll need to pull it out? Like if it's just a coefficient?
What do you mean?
For the upper bound.
Oh, like if it was 3x? Yeah, how about that? Yeah, let's add another one. Oh, whoops, we've been recording this whole time. Who knew? All right, whatever. Yeah, good idea. So okay, maybe I'll switch up the letter. H of x is equal to the integral from 0 to 4x of, maybe we make this one a little crazy or something. Cotangent t times e to the t minus 1. I think that would be a good one. And we want h prime of x, and you're like, oh no, this is going to be really bad. I'm going to have to remember the derivative of cotangent, which you do need to do. I'm going to have to use the product rule. That's not true. You're not going to have to do any of that. So it's going to be, I'm going to take that 4x, and I'm going to throw it in wherever I see t in the integrand. And then I'm going to need to multiply by the derivative of 4x with respect to x for the chain rule, and that's just 4. And that's it. Okay, no product rule. I said cosine, but I meant cotangent. Trust me. Oh, and I know that one's, here we go. Where's my eraser? Yes, not cosine, cotangent. Yeah, and then like I was saying, the free response is very common for this. Let me just kind of set one up, and I won't make you watch me set it up. All right, here's a good one. Here's f of x, and I kind of messed up and didn't put in a y-axis, and I put it in a place where it didn't make much sense. But I'm just telling you that the height here is 2, and the height here is -2. And kind of in a hurry right now, so I'm not going to sit and redraw the graph. So suppose we have the function g of x equals the integral from 2 to x of f of t dt. And that we also know that the areas of these regions are, I don't know, that would be a width of 5 and a height of 2, so it's less than 10, maybe, I don't know, 7. This looks like a little bit less area. I'll say that's got area 5. And this has got area, well, what would we think? Probably less, maybe 3. That should be fine. Okay, some questions I can ask. First of all, I think just what is g of 8? G of 8 is the integral from 2 to 8 of f. And so it's going to be -5. The amount of area, the net signed area under the graph of f between 2 and 8 is going to be -5. Okay, I could ask you for g prime of 5. Okay, now one of what I recommend that you do right at the beginning of one of these problems, and I actually recommend that you do it in each part of it, but the first thing you should do is say, okay, I know what g prime of x is. I can take g prime of x, I'm going to take x, throw it in wherever I see the dummy variable in the integrand, and that's going to be f of x. And g prime equals f. So g prime of 5 is going to equal f of 5, which is looking like -2, right down here, the height of the graph. Okay? If I asked you for g double prime of 5, that looks like it would not exist because I tried to make that a sharp corner. Okay, but I'm not gonna say that. What I will ask is, what is g double prime of -1? Okay, and you can't see that, but there it is. Okay. If g prime of x equals f of x, then g double prime is f prime. Okay. And g double prime of -1 is going to be f prime of -1, which sure looks pretty flat there, and I'm going to say that's 0. Okay. Let's just say there's a relative maximum somewhere of g. Okay, well, that would be a place where g's derivative, which is this, going from positive to negative. Okay, so that's going to be right here at 2, because g prime, which is f, went from positive to negative. So at x equals 2, because g prime, which I know is equal to f, goes from positive to negative. Okay. It's always good that you say, I mean, you can just say g prime if you've already declared that it's equal to f, but it's always good to just make sure that the reader remembers that you know that the derivative of g is f in this case. All right. What else? I mean, there's definitely like increasing, let's say decreasing and concave up. Okay, I'm going to need right on, because I used up the whole screen, but. Okay, decreasing is where the derivative is negative. So that will be where f is negative, so it's somewhere between 2 and 8. Concave up is where the derivative is increasing. That's one way you could think of it. So that would be, you know, between 5 and 10. So overlap would probably be 5 to 8. Or you could say concave up is where g double prime is positive. That's where f prime is positive, so where f has a positive slope, again right here. So where f is both negative and positively sloped, that's 5 to 8. Okay, we can call it the open interval 5 to 8. We could call it the closed interval 5 to 8. We don't care about that. Okay, and just a second. The only other thing, you oftentimes have to do an absolute maximum or an absolute minimum with this, but for the sake of time, I'm not going to do that in this video. If you want to go back and look at the example videos, I've done a lot of them in this unit. So let's move on to 7.2. Okay, these pretty much almost always take the same form. It's the rate in, rate out for your response question. Now, there is something else when we talk about position, velocity, acceleration in a minute, but I'm going to say, you know, suppose, and those of you that were sitting in my class, you know, in the past few days, you'll recognize this example. It's the exact same one I did then, and it's still valid. Students are entering the library at a rate of f of t students per minute. They are leaving the library at g of t students per minute. And at t equals 0, there are 15 kids in the library. Okay. So I could ask you about the number of students or kids entering the library between t equals 0 and t equals 30. Okay. And we would find that by integrating the rate in. Okay, so I'm going to integrate from 0 to 30 f of t dt. Okay. If I'd asked you for the number of kids that left between 0 and 30, you'd have integrated g of t from 0 to 30. Okay, is the total number of kids increasing or decreasing at time t equals 15? Okay. Now, you know, maybe eventually I would write a total number of kids function. Maybe I'll do that right now. So the number of n of t is going to equal the starting number of kids, which was 15 children, and maybe just to avoid any sort of confusion, I'm going to change this to t equals 12 minutes to avoid confusion with 15 minutes, 15 kids. Yeah, 12 minutes. All right. So it's 15 plus the integral from 0 to t of rate in minus rate out, f minus g. And except t is already my variable for time, so my integration variable will be x, or a, or whatever you want it to be. Just not t, and not capital N. Preferably not capital F or capital G either. All right, so if I want to know if the number of kids is increasing or decreasing, I could take the derivative of this function, or I could just take f of t minus g of t to think about the net rate, or I could compare f of t and g of t and see which one was bigger and let that one tell me. Okay, so what I'm going to just say is I'm going to consider f of 12 minus g of 12, and if that's a positive number, then the number of kids is increasing, and if it's a negative number, then the number of kids is decreasing. Okay? What is the number of kids in the library at time t equals 60? Okay? That's where we're going to have to start with our 15 and then add in, really what we're doing is we're going to evaluate n of 60. So maybe I'll just write it like that. And that's going to be equal to 15 plus the integral from 0 to 60 of f of t minus g of t dt, f of x minus g of x dx. It's all the same thing. Rate in minus rate out is what we're integrating. And this is all stuff that we can do on the calculator. Okay? Usually the kind of next thing would be find the absolute maximum number of kids in the library at time t equals 60. But again, for the sake of time, I'm not going to do that. And if you don't have f and g, it's the candidates test, the closed interval test. You need to check the endpoints. You need to check the critical points. Okay, so places where the derivative, f minus g, where that equals 0, we would need to consider that as a potential for an absolute maximum or an absolute minimum. We would also need to consider, if we were saying on the time interval 0 to 60, we need to consider n of 0, which we already know is 15. And we would also need to consider n of 60, which, with any luck, you have already computed over the course of the problem. Okay? So that's the rate in, rate out for your response question. The other thing, and it's really like 7.2, is the given velocity or given acceleration finding and an initial velocity or an initial position, recovering a different position. Okay, so suppose velocity of an object is equal to t e to the negative t sine t, something that's hopelessly anti-differentiable, or not, it's hopeless to anti-differentiate this thing. And this one actually might be anti-differentiable, but 3 products, you don't want to do that. And maybe x of 5 is equal to 1, and we want to know what x of 3 was. So that's where we're going to use the, f of b equals f of a. So x of 3 equals x of 5 plus the integral from 5 back to 3 of the derivative of x, which I know is velocity, with respect to time. And that's a job for the calculator, and I've got one here that doesn't work. Let's see if I've got a big pile of them over here. Hopefully one of them works. Yeah, there we go. All right, so I'm going to say x of 5 was 1, so 1 plus the integral from 5 to 3 of velocity is t e to the negative t sine t. Make sure you're in radian mode when you hit that sine button. And then 1.078. Always 3 decimals in this class. Okay. I could also do this with a given acceleration. If they gave me an acceleration in time, maybe I'll do that. A equals the 4th root of t to the 6 plus 2. And the velocity at time 0 is equal to 5. What is the velocity at time 2? Okay. That would be where we would say, all right, velocity at 2 is going to equal v of 0 plus the integral from 0 to 2 of the derivative of velocity, which is acceleration, dt. And, you could say 5 plus the integral from 0 to 2 of the 4th root. Okay, 4th root, I would do that in the calculator by taking t to the 6 plus 2 to the 1/4 power, or the 0.25 power. That's how I would do it. But, again, I'm not going to do it for the sake of time. I'm already at 19 minutes. That's all I got for you for Unit 7. If you're interested in Unit 6, I've also got that video, but presumably, you've probably already watched that one.